Have you ever Googled a star, like our sun, and seen this little spectral specification tab? Have you ever wondered what this specification means, and how many different types of stars there are? Today I'm going to explain this classification. When it comes to stars, there are a few things that are used for this classification. That is their temperature, /spectral range, and their luminosity. Scientists use different classifications for these two things. Temperature is divided into a letter system with 7 letters, O, B, A, F, G, K, and M, with O-type stars being the hottest and M-type stars being the coolest. While in most stars it is directly related to temperature, this range actually looks at the spectrum of a star and which element lines are the strongest. These letters are then divided into 9 more segments ranging from 0 being the hottest and 9 being the coolest. These represent the most common stars in the universe. However, there are 4 types of stars that fall outside this main sequence. And these are white dwarfs, classified with D, Wolf-Rayet stars, classified with W, stars with equal parts carbon and oxygen, classified with S, and carbon stars, classified with C. Their luminosity, which is almost directly tied to the radius, are divided into classes. Class D, Class SD, Class B, Class IV, Class III, Class II, Class IB, Class IAB, Class IA, and Class 0. I'm going to show you stars under each classification and stage, so you can understand what the spectral classification means. Starting off with these smallest main stage stars, red dwarfs are the coolest and smallest stars, and mainly fall under the MV class. Red dwarfs can have a surface temperature of between 2300 and 3900 Kelvin, and a radius of around half that of the sun, emitting 1/10,000th the luminosity. Because of their size and temperature, they can stay in their main stage for much longer than stars like our sun, with lifespans far exceeding the current age of the universe. On the complete opposite temperature spectrum, we have white dwarfs. While not technically stars and are actually stellar remnants, white dwarfs have a wide range of temperatures, as they aren't burning fuel to maintain temperature and are actively cooling down. The coolest white dwarf we know of is the companion to the PSR J2222-0137 pulsar, and has a surface temperature of around 3000 Kelvin, which for a white dwarf is too cool to measure a luminosity. However, the newly formed remnants can exceed 150,000 Kelvin and are typically DO to DA. Typically, the O to M classification almost directly refers to temperature, but is actually linked to things like Balmer lines in the spectrum of a star. In an A-type star, the most dominant lines are hydrogen lines, like in the star Sirius B, which has a surface temperature of 25,000 Kelvin, but is an A2 class star. Pulsars, or neutron stars, like white dwarfs, are also stellar remnants. However, these remnants were born out of much larger stars and therefore have a lot more energy to radiate out. These stars can be very bright and hot, but due to their composition, they do not fall under the O to M scale. While their surface temperature, which can be in the millions, is easily in the O temperature scale, they do not have spectral absorption lines, as they are made out of neutrons themselves. Due to their extreme heat, these stars, when young, can outshine every type of star and even outshine entire galaxies in some cases. Orange dwarfs, or K-type main sequence stars, like Alpha Centauri b, are spectral class K main stage stars which burn at a lower temperature than stars like our sun. These stars typically have a mass between 0.6 and 0.9 times that of our sun, and surface temperatures ranging between 3,900 and 5,300 Kelvin. These stars are particularly interesting when it comes to the search for extraterrestrial life, due to their stability and long lifespans, staying main sequence for up to 70 billion years. They are also 3 to 4 times more common than stars like our sun, which makes them more abundant, and due to this abundancy and being around the right temperature, they are perfect for habitability. Yellow dwarfs, or G-type main sequence stars, are stars like our sun, which have the spectral type G. having a mass between 0.9 and 1.1 times the mass of our Sun, with a temperature between 5,300 and 6,800 Kelvin. Our Sun is a G2 V-type star and has a surface temperature of 5,800 Kelvin. These stars last for less time than the orange dwarfs, with Sun-like stars burning hydrogen for 10 billion years. These stars are also good for the search for extraterrestrial life, though less promising than orange dwarfs. F-class main sequence stars are hotter than G-type stars, being between 6,000 and 7,300 Kelvin, and are around 1.1 to 1.6 times the mass of the Sun, spending an even shorter time in their hydrogen-burning main sequence phase, spending 2 to 6 billion years fusing hydrogen into helium. Notable examples of these stars include Procyon A, which is an F5V star located 11.46 light-years from Earth, and Gamma Virginis, which is a binary star system with two stars of roughly the same size and temperature, both being F04 stars, F05 type stars. F-class stars are likely the last type of star that will be able to support life, being the least likely of the last three to support it due to their intense UV radiation. A-type main sequence stars are the first stars starting to get into the blue range, typically being white to very light blue. A-type stars have a surface temperature of 7,300 Kelvin to 10,000 Kelvin, and measure between 1.7 and 2.1 solar masses, staying main sequence for around a tenth the time the Sun does, lasting for roughly a billion years. This is also the first main sequence star where it is highly unlikely for it to support life due to the intense levels of X-rays, likely sterilizing any chance. Notable A-type stars include Sirius A, which is the brightest star in the night sky and is a A0MA1VA type star, located 8.6 light-years from Earth. B-type main sequence stars are blue-white stars that have a surface temperature ranging from 10,000 to 30,000 Kelvin, and range from being 2 to 18 times the mass of the Sun, much rarer than A-type stars. They also last a lot less time, staying main sequence for 20 to 400 million years due to their short lifespans, intense UV radiation, and massive stellar winds. These stars make it practically impossible for life to survive. A notable B-type main sequence star is Algol, which is a B8V star, a part of a 3-star system. O-type main sequence stars, the rarest main sequence star, with there only being around 20,000 O-type stars in the entire Milky Way, or about 1 in every 12.5 million stars. An O-type main sequence star has an incredibly short lifespan for a star, at 1 to 10 million years. These stars are between 18 and 90 times the mass of the Sun, and have a surface temperature typically between 33,000 and 50,000 Kelvin. This is now squarely in the range of impossible to support life, as these stars are incredibly short-lived and give off very high amounts of UV radiation. A notable O-type star is Orion A. This star is a part of an exceedingly rare quintuple star system. Orion A is an O9.5V type star. Subgiants, which are classified with an IV, are stars that are brighter than main stage stars of the same spectral type, being 2.5 to 4 magnitudes greater. Subgiants can be in the spectral range from O to M, and it mainly just depends on the predecessor star. This star is the bridge between main stage stars and giants. These stars are less abundant than both, and fill the size in between. The giant stars, classified with III, can come in every range of stellar class from O to M, but what I am going to look at is the extremes, the red giants and the blue giants. Red giant stars are what our Sun will become later on in its life. When our Sun runs out of hydrogen and starts fusing helium, it will begin to expand to around the radius of the Earth's orbit. The Sun will cool to the K2M range, with the surface temperature changing from 5,800 Kelvin to 2,500 to 3,500 Kelvin. Due to their size, these stars are much more luminous than their main sequence counterparts. Blue giants, while smaller in radius than red giants, due to their greater mass and temperature, have greater luminosity. Blue giant stars come from O or B-type main sequence stars after they've used up all their hydrogen. Notable red giants are Gacrox, a 3.5M III star, and Aldebaran, a K5 III star. And notable blue giants are Beta Centauri, a B1 III star, and Mimosa A, a B0.5 III star. Bright stars are class II stars, which ride the border between being a regular giant and a supergiant. Bright stars are more luminous than regular giants, but dimmer than supergiants. A lot rarer than their giant counterparts, supergiants are split into 3 different classifications. IB being the least luminous, IAB being the intermediate luminous, and IA being the most luminous. IB stars are 1,000 to 10,000 times the luminosity of the sun and are the dimmest of the supergiants. IAB stars are the middle ground, being between 50,000 and 150,000 times the luminosity of the sun, while IA stars are the most luminous supergiants, greater than 200,000 times the luminosity of the sun. These stars can range in every spectral type, with the hottest and brightest being blue supergiants, and the coolest but widest stars being red supergiants. Hypergiants are on the edge of what stars can become, some reaching hundreds of times the mass of the sun. Hypergiants, like all other giants, can come in a range from O-type to M-type and have the classification 0, LA-0, or LA+. Stars of this magnitude can range from hundreds of thousands to millions of times the luminosity of the sun. Some of these massive stars include BP Crucius, a B1 LA+ star, a blue hypergiant, R Puppis, a G2 0-LA star, a yellow hypergiant, HR 5171, a K0 0-LA type star, a yellow supergiant, and Mu Cephei, an M2 LA to LA+ hypergiant. Wolf-Rayet stars are extreme even in comparison to some hypergiants. WR stars are a rare, heterogeneous set of stars with unusual spectra, showing high amounts of ionized helium and highly ionized nitrogen and carbon, with surface temperatures ranging from 20,000 to 210,000 Kelvin. The brightest and most massive star we know of in our entire universe is R136A1. This star is a Wolf-Rayet star with a mass 291 times that of our sun, and a luminosity 7 million times that of our sun. Its classification is a WN5H type star. So there you have it. That's all the stars and their spectral types and meanings, going from the smallest to the most massive. I hope you enjoyed, and I hope to see you next time.